Dear friends, in last video we have completed the postulates of valence bond theory and also discussed the formation of sigma bond and pi bond. Today we have to see how valence bond theory succeeded in explaining the structure of polyatomic molecules or bonding in polyatomic molecules like ammonia and water. But the same theory failed in the case of methane. We have to see them one by one. At first, you have to consider ammonia. In ammonia, central atom is nitrogen with configuration, valential configuration of 2s2, 2p3 and can be written as 2s2 and 2p3. Here you can see 3 half-filled orbitals. So they can form 3 covalent bonds. And for bonding, nitrogen need 3 hydrogen atoms. First hydrogen, configuration 1s1. Second hydrogen also 1s1. Third hydrogen also 1s1. First covalent bond takes place between nitrogen and first hydrogen. Half filled P2, 1s of hydrogen, that is this bond. Second one is second half filled orbital of nitrogen with the second hydrogen. Then one more bond is established. And third one is this. And additionally there is a lone pair. Due to repulsion, lone pair bond pair repulsion, lone pair to bond pair repulsion in this side also and this also, there is a decrease in bond angle from 109 degree 28 minute to 107 degree. This bond angle is also reported in VSEPR theory. VBT clearly explained how 3 sigma bonds are formed in ammonia between nitrogen and 3 hydrogen atoms. If you come to water, which is central atom, oxygen is the central atom with configuration 2s2, 2p4. Box representation is 2s2, 2p4. This is the valential configuration of oxygen, which has 2 half-filled orbitals. So they can form 2 covalent bonds. When hydrogen comes, first hydrogen 1s1 and second hydrogen 1s1. Here overlap takes place between this half-filled P and first hydrogen, then second P and second hydrogen. So oxygen can form 2 sigma bonds with hydrogen. Pictorial representation can be made more attractive like this. In the case of ammonia, nitrogen possesses 3 half-filled p orbitals which are mutually perpendicular to each other. X-axis, that is px, py and pz. Here you can see one hydrogen, another hydrogen, electron of nitrogen, this is of hydrogen, third hydrogen, electron of hydrogen, electron of nitrogen. This way bond is formed. In the case of water, structure is like this. Additionally, you can see two lone pairs also. Lone pairs also. But more importantly, we have to write like this: oxygen having two p orbitals, half filled p orbitals. One is like this and one is like this. Each of them carry one electron. Here one hydrogen comes with one electron. Here other hydrogen come with one electron. So this is one axis, this is another axis. Both the axes are internuclear axis. Why? This is nucleus of oxygen. This is nucleus of oxygen. This is nucleus of hydrogen. This is also hydrogen. Here you can see two sigma bonds. One is from oxygen to hydrogen, other is from oxygen to this hydrogen. Both are sigma bonds because bonds both have been formed along the internuclear axis. This is one axis. Here you have one nucleus, another here. So it is internuclear. Here one nucleus, here other nucleus. That is also internuclear axis. So orbitals are moving along the internuclear axis and both bonds are sigma. So ammonia contains 3 sigma bonds, no pi bonds. Water also contains 2 sigma bonds, no pi bonds. If the same thing we are now applying in methane. Before proceeding to that stage, you have to see what kind of sigma is there. This is sp. This is also sp. This is also sp. This is sp. This is also sp. So 2 bonds are identical. Here 3 bonds are identical. For methane, central atom is carbon. Configuration in valence shell is 2s2 2p2. 2s2 2p2. Here we have only 2 half filled orbitals. But from this formula, it is very clear that we need to have 4 orbitals as half filled. So carbon now excited state, this electron excited to this orbital and become 2s1 2p3. Now we have 4 half filled orbital after excitation of the carbon. Thereafter we have 4 hydrogen atoms, each of which has a configuration of 1s1. One hydrogen here, another hydrogen here, third one and fourth one. Now bond formation start from S of, which is 2s of carbon to 1s of hydrogen, 2p2 1s, 2p2 1s, 2p2 1s. 4 sigma bonds are formed. Carbon 4 sigma bonds. 1 2 3 4. If it is numbered H1, H2, H3, H4, H1, H2 here, H3 here, H4 here, we will get tetrahedral shape. But here is a problem. What problem? We can see. If we consider the nature of sigma bond formed in methane, first bond is formed between S and S. S of carbon, S of hydrogen. That is S sigma bond. Second one is Sp. This is also Sp. This is also Sp. So in methane we have 1 S sigma and 3 Sp sigma bonds. But this was not the condition in ammonia. There we had 3 sp. In water also we had 2 sp, but here 1 ss and 3 sp. Definitely there is a difference in the bond length of ss and sp. Compared to ss, sp bonds are more elongated since p is dumbbell shaped and directional. So in methane we can expect two kinds of bond length. SS bond is a short bond and 3 sp bonds. If this theory is correct for methane, we can get two kinds of bond length in methane, but experimentally we have proved that, or we have got the value as same in 4 cases. All the 4 bonds in methane are identical. So that observation could not be explained successfully by valence bond theory. That was the first drawback of valence bond theory. To overcome this drawback, we have started hybridization that we can discuss in another class. Thank you.